Okay, add velocity and acceleration vectors at each location, right? So, which way is the velocity point at A?
Towards B straight.
Towards B. Why towards B, Rex?
Because
Velocity is the change in what?
distance over time. I think.
Close. Not just displacement, right? So our change in position, our displacement is that over time is our velocity. So from A to B, the object is moving from A to B, right? So its velocity is kind of towards B, right? That'd be more of average velocity. That's good enough, though. Yeah, at B, which way is the point?
Towards C.
Towards
So
C.
we're supposed to put a B on it?
Does the vector get larger or smaller?
Larger.
Larger. What about C? Larger, and which way does it point?
D.
Towards D. What about D?
E.
Larger and towards E. What about an E?
Large.
Larger, which way?
It doesn't have.
To the side.
There's no direction anymore?
It's to the side.
Dude, that way?
No,
No,
it's
it's
down.
Down, okay.
Yeah,
I need to use
down.
this, I need to use it.
Okay, oh, and then,
I don't have any erasers.
so, A, B, C, D, and E. Does that make sense?
I didn't move.
Okay. Now, which way is the acceleration pointing?
Down.
Down. Why is it pointing down?
Just gravity.
Because of gravity. Right? So the acceleration is downward because of, what was that word again? Gravity. So, Kyle, think of inertia. All right.
You'll be right.
Does gravity change in each of these locations?
No, gravity's always there.
It's always the same magnitude and the same direction, right? It's going to be the same magnitude. It's going to point down. So here's our acceleration. Kyle's not inertia still.
He said it eventually. He'll get it right one time. Remember when you
I think we're done talking about inertia today.
and Pat was like, who's inertia?
That's a black girl.
Okay. All right. So the green vectors represent the velocity.
Inertia.
The blue
I don't remember
vectors
to do that.
represent the acceleration. Does that make sense?
Someone's really probably named inertia.
Now, what does? Okay. I'm glad you had to talk about physics concepts. Just not the right context. All right. Okay, settle down for a second. Okay, we all ready to talk about this?
No.
Okay, because if we don't understand what we're going to talk about here, that's going to make what we're going to talk about after this more difficult. Okay? What's that?
So who's right? Look at that.
All right. So, does acceleration change from A to E? No. It's always pointing down. It's always 9.8, right? Yeah. Now, what does the acceleration do to the velocity of the cannonball?
Makes it go faster.
Makes it go faster, right? The acceleration increases our speed because part of our acceleration is in the same direction as the velocity. Because there's a part of this acceleration that points in the same direction as the velocity. Or I could say it the other way. There's a part of the velocity that's in the same direction as the acceleration, right? Right? And as the object is falling, that part that's in the same direction as the acceleration gets longer and longer and longer. Because the object is accelerating in that direction. So the speed does increase. What else happens here? What else does the acceleration do? Why doesn't the cannonball part A just keep going on the same path? Because this cannonball is launched this way. Right? So why doesn't it stay on that horizontal path? Gravity pulls it down. So the acceleration causes the cannonball to turn. Good. Causes the cannonball to change its direction, right? So the cannonball, instead of following that horizontal path, follows this path that kind of looks like a... begins with a P. Parabola. Good. Good, that's the trajectory. Nice. So if there was no gravity, it'd follow this trajectory. But since there is gravity, we follow a parabolic trajectory. Does that make sense?
Yellow terms that we were
So that kind of, you might get the right answer that way. So do you guys remember doing this?
No. I wasn't here.
You weren't here? Okay.
I was.
Don wasn't here either, but she remembers. All right.
She watched the video.
So now here is a car going on a circular on-ramp. Okay? So this is a circular on-ramp, like for getting on the highway.
We're looking from the sky.
Yep, we're looking from the top down. Okay? So what I would like you guys to do is I would like you to add velocity vectors and acceleration vectors to this picture right here.
Can I
No.
do it?
Nope, don't draw on board. Draw on your own. Okay. Now, typically, when you go on a circular on-ramp, I don't know about you guys, but I tend to keep the same speed going on the on-ramp.
I see.
So let's assume that we're moving at a constant speed.
That's hard enough.
Coach, are you
25
learning
miles
about
per hour.
centripetal force right now?
We are.
Nice.
So let's say we're running at a constant speed. So I want you to add the velocity and acceleration vectors at each one of those
You can
locations.
do it, right?
If there's no acceleration,
I'll just
it's
take
a
the
constant
constant
speed.
speed.
Mom, was powerlifting canceled? Did you go?
Well,
it wasn't canceled. Look at this.
Right, Coach, you got your
Right.
class.
You're gonna be on the airman camera.
Hey, I was this way.
Guys, velocity and acceleration. Stop messing with the camera.
Put it down. I don't want my face to be.
Push in the back. Push in the back. Okay.
Randy wants to bring back the packet.
Okay. It's parents' night too, so if you're want to come back for it. All right, you can.
What time is the beach?
5:30. Have your mom here at 5 o'clock for the parents' night.
I'll be there. I'll be there.
So draw velocity and accelerations at each location.
Hey, Branch, do you bring your parents?
I do not bring my parents' night.
Oh, yeah.
Guys, and pictures. Yeah, like go Katrina.
I had to ask a question you didn't answer, so that's
What's
my
question?
fault. Isn't there no acceleration if it's constant?
So constant speed. You think that means no acceleration?
Yeah.
Yeah.
Yeah, no, because it's a ramp. So, it's like this, right?
Yeah. Don't worry about ramps. Don't worry about inclines and declines. Just think about the top view.
Well, I'm just gonna take a guess there.
Just take a guess.
Can I take my mom back? It's really
No, you all done?
Well, look, it says mama.
Jose, you all done?
No.
Look.
Yeah, but you call your mama Mama Duke. So.
Can I take her back?
No.
Yeah, let me text my mom real quick.
No. Because you'll be texting that Kanye boy again.
No, I really need to text her.
Okay. So, velocities. Which way are the velocities at each location? If I'm at A, which way is velocity? Towards B? What about B? Towards E. Now I said constant speed, so are the lengths of these vectors going to change?
No.
What? No, sir.
What about C? Towards D. What about D? Towards D. What about E?
Towards that way.
Okay. So those should all be the same length. Okay. Now, guys, when I say the word tangent, you guys remember what that means?
Yeah, I do.
Remember when we were talking about parabolas, and we were talking about instantaneous speed. We draw a line tangent to the parabola at that location. Like here, that's tangent, so it's parallel to the parabola at that spot, right? Yep, touched it one time. So like right here at the peak, in a horizontal slope, which meant speed was 0. Right, you guys remember that?
Yeah.
Okay. These velocities at A, B, C, D, and E, they are tangent to the circle. Okay, so what that means, this is a part of a circular on-ramp. So there's my circle. At A, the velocity is like this. At B, the velocity is like that. At C, the velocity is like this. Oh, that's not a good tangent one. At D, the velocity is like this. At E, the velocity is like that. Does that make sense?
You didn't draw very good circles for me in geometry.
Yeah, I know. So does that make sense?
Yeah.
So those are tangent. They intersect the circle at one spot in each of those locations. Okay. Now I asked the second question. Can we draw acceleration? Now, Katrina, you immediately had a problem with this. What would you say? What did you say your problem with drawing accelerations was?
It's constant, so there is a one.
What's constant?
The speed.
The speed is constant.
So is the velocity.
Well, speed is the number for velocity, right? So Katrina says the speed is constant. So she can't draw acceleration vectors because the speed is constant, right? Did anyone else draw acceleration vectors?
Gravity. I thought about it.
Gravity. Well, this is a top-down view, so gravity would be into the board. So think about you're the track reporter for like the news, and you're sitting up here and you're looking down.
And the helicopter?
Okay. So gravity's pointing into the board.
I thought about it.
You thought about drawing gravity?
No, drawing acceleration vector.
Anyone?
Drawing outward.
Outward. So Rex says that the acceleration vector would be like this.
What about inward?
I just kind of thought about
Okay. Or
it. Because, like, you know when you're turning like that, you slide in your seat.
oh, so when you're turning like this and you don't have your seatbelt on, and the seats are leather, right? And you kind of slide out the outside, right? You guys ever feel that before? Or when you're turning this, you just kind of think a pull of your body towards the outside of the car.
Yeah.
So that's where you're getting the outward force?
Yes.
Okay. Or the outward acceleration, sorry.
If you drive really slow, you don't feel that.
If you drive slow, you don't feel that.
Like if you go over the speed limit, then you feel it. Like if you go 25, you won't feel it. But,
You guys know more about this than what you think than what you know.
but if you go 40,
Than what you think you do. You know more about this than what you know. I know, that's a weird statement. But you guys know more about this topic we're talking about than what you think you do. Okay, because what you're talking about right now with that, what you just said, Katrina, if I drive really fast, then I feel this outward force. But if I drive slower, I don't feel that. Right? That is a basic understanding of how this whole bucket and water situation works.
I'll still feel the test though.
So, no you won't. Alright? So, we're getting closer though. Why would I have you draw this one first? Because I'm mean and I want you to do projectile motion? No, that's not it. Okay? Why would I have you draw this one first?
Because it gives us an understanding of vectors.
A vector.
Okay, it's accessing your understanding of vectors, velocities, and accelerations, right? Okay. What happens to the velocity of the cannonball here? What happens to its path? It doesn't go this way. It turns, right? Curves. Okay, sorry. It curves in the direction of the... Okay, it curves towards the ground, Amani, because of what force?
Gravity.
Gravity. Gravity pulls us
Down.
down. So this turns in the same direction as the gravity, also known as the, begins with A. Acceleration. Good. A little louder next time, Caleb. So the cannonball turns, Jose.
Doesn't inertia start
Okay.
with the I?
It does. The cannonball turns in the same direction as the acceleration. Does that make sense? Okay. So why would I have you draw this picture and then look at this one? Because if the car is turning, right, is it accelerating?
Yeah. Yeah.
Which way is it experiencing acceleration, Rex? The way that it's turning, right? So this outward one is not correct. The acceleration of this car at each location is inward. It is towards the center of the circle.
The center of the gravity?
Nope, the center of the circular path.
Center of the earth?
Sure, center of the earth. No, towards the center of the circle. All right. So this is a road again. Gravity's down. So at each location, A, B, C, D, and E, there'll be an acceleration that's towards.
So an example like this is going to be on the test.
Maybe.
Well, now I know
How come we didn't take a pretest for this?
We did. We took it with our projectile motion stuff. Because before we had those snow days before the end of the semester, we were going to finish this in there. So we did. All right. Any questions about this? Okay. So, how can we have these green velocity vectors? Now, how can we have these green velocity vectors that are the same length, and these blue acceleration vectors that are obviously there? How can we have them both happen at the same time? Let me say again. How can we have this constant speed but have this acceleration?
They're going different ways.
What do you mean they're going different ways?
Like one's going that way, one's going that way. So if they're going together, they like add to each other. But
Okay, so let's say I had this, and this is my velocity, right? And let's say this was my acceleration.
Ooh.
Would that speed it up or slow it down? It's going to speed it up, right? Because there's a part of this green acceleration that's in the same direction as my velocity, right? Not only will it speed this object up, but it'll also make it turn which way? Down, right? Right? Likewise, if I had an acceleration this way,
it's like going to the
would that speed it up or slow it down? Slow it down, because there's a part of the acceleration in this direction, right? And I'm also going to turn which way? Down, because there's a part of the acceleration downward, right? So where can I have an acceleration for this black vector, right, that causes it just to turn? Caleb? 90 degrees. Perfect. So if, sorry Rex, we got to go on the line, I think I had to finish it. All right. So if our acceleration vector and our velocity vector make a right angle, kind of like just like an x and y axis, there's no part of our velocity that's in the same direction as our acceleration. There's no part of our acceleration that's got us in the same direction as our velocity. And since that's the case, the velocity's magnitude, or the speed, will be the same. But what happens to the direction? It turns. So it is possible for this car to go around this on-ramp at a constant speed and still feel an acceleration. Is that uncomfortable for anybody?
Mine.
Really? Nice. Should turn the camera. But I don't have a waiver for you. So, constant speed, but we experience an acceleration.
Oh, I was gonna ask something.
Oh, ask it. Ask it.
Oh, I was gonna say, like, so when we go up and fix the problems and you're recording, you technically can't do that.
Yeah, I don't record you then.
Oh.
So when you're doing the problems on the board, I never record you.
Oh.
So
What if I walked up with a tardy soap or something?
I make sure.
What if I just put
But you can
that-
get legally sued.
What? Then you're giving me consent. All right. So constant speed here. The car is going around at a constant speed, but is experiencing acceleration towards the center of the circle. And because the velocity and the acceleration are perpendicular, all the acceleration does is change the direction. It does not change the speed. Right? So this is possible as long as acceleration is perpendicular to the velocity. Right? So we can go around that loop at a constant speed as long as our acceleration is perpendicular to our velocity. So if I were to ask you a question somewhere in time and say, is it possible for an object to experience an acceleration and be moving at a constant speed?
I'd say yes.
What'd you guys say?
Yes, as long as the acceleration is moving perpendicular.
Okay, man, completely just repeating what I said.
I'd say yes at the velocity.
What has to be true about the object then?
Moving in circles.
It's moving in a
Oh,
circle.
Circle.
Right? So my bucket of water. When I swing my bucket of water around at a constant speed, all right, is it experiencing acceleration?
Yeah.
Yeah, which way is the acceleration? Towards my elbow, right? And the speed from at each location, up here it's pointing up or down, depending on which way I swing the bucket. Above here it's pointing to the side. Oh, lost some water there. Yeah. Up here it's pointing to the side, right? Over here it's pointing down, right? Depending on where the bucket's at. All right, so does that make sense, guys? Okay. Now, does this car or the bucket, for example, does it experience a force as it goes around the on-ramp? Does the car experience a force?
Sure, why not?
Sure, why not? Well, if we have an acceleration, we have to have a force. Newton's second law, right? F net equals ma. So which way is the net force acting on this car? Towards the center. Why towards the center, Rex? It's going in the circle.
Anybody else?
Because that's the way the acceleration points. Okay, you guys remember this equation? F net equals ma, right? Remember, mass is not a vector, right? So, Eric, what this means is that the force and the acceleration are always in the same direction. So, as this car goes around the circle, it experiences a net force towards the center of the circle. What provides that force? In this picture, this is a car. What provides that force?
I think.
Not the engine.
Turn.
The road.
Turn. The road? We're getting closer.
Acceleration.
I'll let you guys think about that on your own. Okay? Now, when I swing the bucket, what provides the force? No, I want you to think about it.
Your arm.
My arm, right?
Muscles.
So, you're probably thinking now, if you're pulling down on the buckets, how is the water not coming out? Is anybody thinking that? No one is?
We don't care.
You don't care?
Inertia.
Okay, so the inertia is part of it, all right? But the reason why the water is not coming out of the bucket goes to the difference between those two words you wrote up there earlier. Centrifugal and centripetal, okay? And we'll get into that later on.
Which word is it?
Okay, can you tell us?
No, you're excited. I want to keep excited.
So this is gonna unexcite us?
No, I want to excite you. But I want to keep you interested in what we're talking about. So if you're thinking, what word is it? Then maybe it'll keep you motivated. All right. Any questions about these two drawings? None?